My name is Jim Christ. I work for Continuum Analytics on Dask, and we're going to talk today about debugging and profiling. So first, a quick overview for those not in the know. Actually, can I get a show of hands? How many people have heard of Dask before? Awesome. How many people have used Dask? This is also cool. So for those that have not heard of Dask before, Dask is a parallel computing framework. It's written in pure Python, so it's easy to install. You can install it with Conda or pip. Everything works fine. It leverages the existing Python ecosystem. We try to use tools that you're familiar with, like NumPy and Pandas. And we use blocked algorithms and task scheduling. So most of the time, you don't need to know all this. Dask strives to be easy. It tries to be familiar. We have collections like Dask array, which look like NumPy arrays, Dask data frame, which looks like Pandas data frames. Everything should feel very familiar. You can write code that looks familiar. This is using a library called Dask Search CV. Has a reimplementation of scikit-learn's grid search CV. It's just a drop-in. You write normal code, call fit. Behind the scenes, it builds up a big task graph, which is then passed off to the schedulers to run. So most of the time, you don't need to actually delve into the internals. This talk is about what happens when things go wrong, when things don't work as expected. And there's no better way to talk about when things don't work as expected as live coding for the rest of the talk. So that's what this is going to be. So I'm going to be working through a long-form example using some data. This is the airline data set. So you can see we have a bunch of CSV files. These are all flights out of New York in the 90s, so out of the 3 New York airports. I can load it with Pandas. Yep. So using read CSV, we can load and just look at the first file. We can take a look at the top rows. Can I make this a little bit smaller? Is this still readable in the back? Cool. So you can take a look at the D types. This is just a Pandas data frame. We have things in here like the date of the flight, so when flight took off. We have things like the origin airport. If we were to do just the unique airports, you can see that it's just the airports out of New York. So we have 10 CSV files, and the problem we're going to be working through today is doing a resampling by month. So we want to group everything by month and then take the count from each airport. So we want to know how many flights were out of EWR, LGA, and JFK every month in the 90s. So in one CSV, this would be easy. This is just a simple Pandas call. With multiple CSVs, we have a bunch of different ways to do this, and we're going to walk in through that. So the first way would be, I'm going to make this a little bit smaller, just a serial Pandas function. So here we have a function called counts by origin. We're going to loop through all of the CSVs. For each CSV, we're going to load it. We're going to parse the first 3 columns as a date, so we can actually get the date that it flew out. And we're going to store each of the data frames in a list. And then after that, we're going to concatenate them together. And then we can just do Pandas resample calls. This is just common Pandas operations, and return the results. So if I import and by month and by year, counts by origin. And I'll time that using the IPython time magic. So this, if I remember right, takes about 12 seconds. Yep, so 12.9 seconds. And we can even plot the results here. So you can actually see what they came out. And you can see that there were way fewer flights in the 90s out of JFK than the other 2. So this is all fine, and this is all done in serial. But what if this was too slow? Maybe we want to do this much faster. So our first attempt might be to use something called Dask delayed. Dask delayed is a very simple interface. It's a single function. If you wrap delayed around another function, it makes it lazy. It runs later as a task. If you wrap it around data, it makes touching that data lazy. And so you can use this to parallelize existing code with very little changes. So here is our next implementation. You can see we've wrapped delayed around the call to read CSV. And we've wrapped delayed around the call to concat. There are no other changes to this function. So if I go and try to do this again, we can say, and time it. This time, nope, time it. So this time it ran very, very fast. And the reason it ran fast is because it hasn't done anything yet. This has just built up a graph behind the scenes of what it actually needs to do. So to actually time what's going on, we can use dask.compute. So Dask objects have a compute method, but if you're computing more than one, it's best to use dask.compute as the function, and you can pass in both at the same time. So we'll call this. And the reason for that is it can merge the graphs. So by month and by year are both going to be reading. We don't want to read data from disk twice. We want to read it once. So this should take, if I remember right, about 8 seconds. And this is running through Dask, and this is running in parallel. 9 seconds this time. So it's a little bit faster than before, but it's not great. And there is one more big issue with this. So if we look at the graphs, you can use dask.visualize to actually draw out the Dask graphs. And so we can see at the bottom here, we have all the little read CSV calls. And then once they're all loaded, we concatenate them together and we go up. And so the reading is being done in parallel. But if you look closely, we're loading all of the data into memory at once. We're not actually getting any out of core aspects. This is fine for small data sets like this. But if we had gigabytes of CSV files, this would not be optimal. So we might want to rethink our algorithm. We might not want to load all the data and then work in Pandas only in serial. We'd maybe want to do some kind of reduction to each individual frame, concatenate those together, and work with them that way. So if we were to think about our problem a little bit more, we can try again. And so this time, I've broken things out into smaller functions. You can use delayed as a decorator, if you're familiar with the decorators in Python. So I've written a function to load a file. This is the same pandas call we had before. I've written a function to then count the flights. So for each individual file, if you remember, a file is just per year. We're going to count resample per month. So the result of that is going to be a smaller data frame than our original one that's just along the index each month of that year. And the columns are going to be the counts for each airport. We'll then merge them together. We'll concatenate those frames together. So that gets us our resampling by month. And then to get our resampling by year, we just resample across each year in sum. The rest of the code is just looping through. So this is, again, familiar-looking Pandas code, or Python code. We have been able to parallelize things with delayed. And I'm going to run that one. So if we time that again, this took about 6.9 seconds, so faster than before. And if we look at the graph, we can see that we have parallelizing steps where we load each file, and then we count the flights, getting a much smaller intermediate value, which is then merged together. And we can even measure our memory usage with the memory profiler IPython extension. This is great. Memit, if you're familiar with timeit, Memit does pretty much the same thing. And so we could see that we started off with just shy of a gigabyte in memory, and the increment was only 400 or so megs, which is much smaller than the data set we were loading. We didn't load everything to memory at once. Moving on. So let's say that 6.9 seconds is still too slow. We want to be faster than this. So now we want to start profiling. You don't want to guess what's slow. You want to start profiling. So I'm going to use a tool called SnakeViz. How many people have used SnakeViz before? Awesome. So for those that haven't, SnakeViz is a great tool for viewing Python profiling. So I'm going to call compute on our previous graph. And I'm going to pass in Git. So Dask has multiple different schedulers. So far, we've been using the thread pool scheduler. For profiling in this, we want to be using the serial scheduler. This plays better with common Python profiling tools like SnakeFizz. We'll get into Dask-specific profiling tools in a second. So running this again, and in just a few seconds, this should open up another window in my browser. Awesome. So increase the depth, and let's go to that presentation. So this is walking down the stack of what we have. So up at the top here, first couple bars, this is all Dask internals. We have some stuff that's inside the scheduler. This isn't super useful for you for profiling. But if we go down a little bit further, we see one of our first functions we wrote. We wrote this load file function for loading from disk, and we can see it's taking 9 seconds of the time. It's taking most of the time here. So if we can make that faster, we can make our whole execution faster. So the solution here is just to use Pandas better. So we're going to pass in a few extra things. Pandas has a keyword argument, use calls. To read CSV, this can be a lot faster. You don't have to read in all of the different columns. We can just read in the ones we care about. In this case, it's the year, month, day, and the originating airport. We'll pass in dtype to specify the origin as a category. Categoricals can be faster for some things in Pandas. Maybe this is faster now. And the rest of our code is the same. We have the same tasks. So, and we'll run that again to build it, and time. And oh no, we got a bug. So one nice thing about Dask is you can run things locally. And Dask is pure Python. Dask plays well with Python. And so you can use our normal Python tools for debugging. So in this case, we can just start up PDB, automatic PDB calling. When we run into an error, IPython just drops us into a PDB console. So looking around, we're seeing data type not understood. Locally, I see a dtype variable. Let's take a look at that. And let's take a look at the type of that. And it's a set. So when I specified this, I didn't put in a colon. I had a comma instead accidentally. So fixing that. We can build it again. And time it again. And so we're now down to 4 some seconds, which is a lot faster than before. This still isn't as fast as we'd expect, though. I am running on, I have 8 processes, or 8 cores on my computer here. And we're only getting about 2 to 3x speed up. We're not getting the parallelism we'd expect. So Dask, for parallel profiling, has a bunch of tools in the Dask diagnostics module. So I'm going to import a couple of those. Profiler is for task-level profiling. Resource profiler is for measuring memory and CPU usage. And this is just for plotting. So these are used as context managers. So with profiler as resource profiler, I'm going to tell it to sample every quarter second. And we'll do the compute call. Everything in this block is profiled then, by month and by year. And then we can plot those. Cool. Can we make this bigger? So what we're seeing here are 2 plots. The top plot here is task-wise. So each of these bars, each of these is a worker. So one worker thread or one worker process, threads in this case. Each of the blocks right here is a task. So this is the load file task. This is reading from disk. Here's some of our aggregations, counting flights. On the bottom down here, we see CPU usage and memory usage. So CPU is in purple, and we can see in the beginning we're getting close to 4 cores being used. I have 4 actual cores on my machine, so that's what I expect. I'm getting almost full parallelism, and then it suddenly drops down to just being serial, even though up top we still see tasks running at the same time. Does anyone have an idea why this is happening? Not quite. It is, yeah. It's the global interpreter lock. So Python has this thing called the global interpreter lock, which makes that you can only run Python code in one thread at a time. Certain libraries like Pandas and NumPy can release the interpreter lock, so you can actually get thread-level parallelism. But in this case, we're not. So one nice thing about Dask is it makes it really easy to swap out schedulers. So in this case, we can just try with the multiprocessing scheduler. So running that again. You specify schedulers, as you saw before, by passing in the get keyword. So I'm going to say use the multiprocessing scheduler instead. I haven't had to rebuild the graphs. We're just calling compute again with a different thing. And we can see this is a lot faster. And we can also see we're getting pretty close to full parallelism across all 4 processes. So this took about 1.5 and some change seconds to run. So looking at this, though, we still have spending a lot of time in I/O. We're still reading from disk. It's taking most of our time. So what if we were to use different storage? CSV is slow to parse. There are faster storage methods. So Dask has ways to read from the format Parquet. So in this case, I've already written the data out to a file called flights.parquet. We can read it in with Dask data frame and do the same operation using Dask data frame to do the computations. So from 6 import, I've done this slightly different. DF is now passed into counts by origin, so just a slightly different signature. And we can call, or we can time that. Oh. So milliseconds at this point. And this is all running using threads. So we've taken this from running in 14 or so seconds down to almost nothing by profiling and trying to optimize things. We can scale out. So what if we had a lot more data? We might want to run distributed. Dask has a distributed scheduler. You can create a local scheduler by importing from distributed and creating a client locally. So this is going to be spinning up 8 different processes on my local machine by default. And then I can also when you create a client, it takes over as the default scheduler, so I don't have to pass in Git. This is running distributed by default. One nice thing about the distributed scheduler is it has a really nice dashboard. This is all written in Bokeh, great plotting library. So if I run compute, you can see tasks appear here. This is similar to the diagnostic spots we were seeing before. So we have one per worker. Each rectangle represents a task. This isn't super informative, though, because it's taking up our things run so fast. We're not seeing everything. So to do a little bit better demo, I'm going to create another computation using Dask array. Random, we'll say 10,000, 10,000, I don't know, chunks. Cool. So over here, we're seeing the tasks as they appear. This is all running in real time. Red is data transfer. So red means serialization from one worker to another. Up top, we can see bytes stored across the whole cluster. Things turn orange as memory usage gets higher than it should. Eventually, it'll turn red. If you get too high, that means it's writing to disk. The panel over here is tasks processing for worker. And down at the bottom, you can see progress bars running along for each of our individual tasks. So we have one for sum, one's for tensor dot, so on. We have other tabs. You can look at the system usage. This is going to show CPU usage across the cluster, memory usage, bandwidth, and such. Individual workers are in this plot, memory usage per worker, different host names. Once everything's done, you can look at the static task plot if you wanted to look back in time and see what was going on. Of course, since this is Bokeh, it's all interactive, so you can zoom in and investigate different sections of the graph. We're seeing a lot of red here because we're serializing with NumPy. And NumPy can run better in threads because NumPy releases the GIL. So I have set up another cluster locally. So I can create another client. This one's set up to run with more threads than processes. Before we were running with just single process, with just one process per worker. Now we have fewer processes and more threads. So we can do compute again. Let's open up that. And now we're running on here. And you can see a lot less red because we're not having to serialize as much. We can use the shared memory on each worker. Oh. Interesting. Well, live coding. Anyway, I guess we're running short on time, so I'll just conclude. So summary. Think about your problem. There may be a better algorithm. We started off by reading everything in from disk, but rewriting our code, we were able to load things incrementally. You want to maximize parallelism, so you want to give Dask as many opportunities to do things in parallel as possible, and you want to minimize the intermediate data size. You don't want to be serializing large objects between workers. Think about when to call compute. So we talked about using Dask.compute rather than the compute method to compute more than one thing at once. Dask can be smart and merge graphs, so we don't repeat computation. We don't read from disk twice. You can use Dask.visualize to inspect the graphs, to look at what's going on underneath them. Profile. Profiling is useful. Don't guess what's slow. Profile it. SnakeViz and Line Profiler are great for profiling individual tasks. And then the diagnostics for single machine and the distributed dashboard for parallel across a cluster are great for measuring performance in parallel. Debug locally. Dask works fine locally, and PDB works great with Dask. You can drop in and debug normally how you would. Scale out if needed. I didn't mention persist. Ran out of time, but persist can be used to store graphs along the way. You can store smaller results in memory. So we were talked about using a faster source for reading from disk. You can store things in memory and skip the disk reading step. Use the diagnostics page, as I mentioned. The distributed diagnostics are great for figuring out what is slowing you down. Acknowledgements. Dask is an open source project. We have a large developer community. They've helped make all of these pretty tools that you've seen. The larger SciPy developer community has helped us figure out what's important. Our work is funded by the Gordon and Betty Moore Foundation and the DARPA X-Data program, and my employer is Continuum Analytics. Questions?